Great. I think we'll begin. So yes, good morning again. Thank you for joining this webinar. It's part of a series of webinars organised by AI for Soil Health, taking place over the late summer into the autumn. This one is predicting the future of soil health with AI. I'm joined by three people who are part of the consortium who will be giving presentations. So Professor David Robinson from the UK Centre for Ecology and Hydrology, Dr. Emmanuel Ligato from the European Commission's Joint Research Centre, and Dr. Mehdi Afsar from the Hamburg University of Technology. Before we can move on to the presentations, I do have a certain amount of housekeeping. First of which is that today's webinar is being recorded. We will be able to share a link with you after the event is complete, and we would welcome you to revisit the content yourself and share it with colleagues. The format of today's event will be as follows. So we have the introduction, speaker presentations, an audience Q&A, and then some concluding remarks, sort of wrapping things up. We invite your comments and questions. Please look at the Q&A chat box on your screen. If you think of a question for the speakers at any point, just type it into the Q&A box, and I will try and pose as many of them as possible to our speakers during the Q&A discussion portion of the event after the presentations. We have Maddie on hand. I'm sure many of you have know Maddie, and she's on hand for any technical difficulties. I'm hoping there won't be many, but you never know. And message in the chat, and she will try to help. So yes, introduction to AI for soil health. The health of soils across Europe are under threat. A transition to a sustainable future is possible, but the risk of innovation to land managers is high. We need to understand which farming practices work and which do not to protect the environment and make businesses more resilient in the face of changing times. AI for Soil Health aims to help farmers and land managers to measure soil health without the need for laboratories. Additionally, we want to help policymakers explore the changes they make in farming and land use, giving them up-to-date modelling on their plans and reliable data on the impact that they're making. AI for Soil Health works with stakeholders to co-design, create and harness digital technology to support pan-European efforts to halt and reverse soil health decline. We want to achieve a world where every farmer and land manager can do their own on-farm experimentation into soil health. This means using the latest scientific expertise to build the digital infrastructure to support them so they can innovate and track their actions in real time. Before I introduce our three speakers, we have some quick questions for you, our audience today. We're using Menti today. Hopefully you're familiar with it. So we're using it to be able to engage with you and get some feedback. So please either scan the QR code on screen with your phone or follow the link in the chat. The code you need to enter is on screen, 577989999. The questions that we have, what are your domains of expertise? Be really useful to have that information. Secondly, so soil health science, data science, AI machine learning, land use management practices, land use management policy. Expert audience. It's good to see. So the second question is, what scale do you predominantly work on or with? Good, a broad range. And then the third question is, what is your main motivation to join this discussion today? That's a free to say what you want question. Excellent. It's a broad range of interests, and I hope we will be able to cover most of these areas. But obviously, there's plenty of time for Q&A, so you can ask your personalised questions after the presentations. I feel we can move on to the presentations now, and I'd first of all like to introduce Professor David Robinson. David is Principal Research Scientist at UKCEH Centre for Ecology and Hydrology, specialising in soil science and monitoring. He's responsible for UKCEH soil observatories and elements of national soil monitoring in the UK. In addition, his research interests focus on soil physics, including soil hydrology, structure, and erosion. And moreover, he investigates soil physical function and its interplay with biology within the wider context of soil monitoring and ecosystem service assessments in response to climate change and land use drivers. So I'll hand over to you, David. Thank you.
Okay, that should now be shared. And okay, well, good morning, everybody. And it's nice to be here. Thanks for the invitation. This is work on soil quality and health, on conceptual frameworks that we've been developing in order to aid with setting the frameworks for AI and the interpretation as part of the AI for Soil Health project. So Grant Campbell, Pete Smith, and myself have been leading this particular component of work on frameworks, and that I'm going to be talking about today with input from most of the team across AI for Soil Health project. So I thought starting with the idea of quality. So why are we bothered about quality? It's a framework that we use often because it enables us to get at what is better or what is worse, and to be able to assess a system. And this idea of quality often underpins much of the monitoring and indicator selection that we do in order to determine the status of soils. So it helps determine how we select indicators, how we select an AI framework, how we interpret indicators, including the thresholds, and how we analyze them. So making sure that we're all talking about the same thing. And this is the problem when we start looking at quality, that in many ways it's a bit ill-defined. So when you look into a dictionary, you can find multiple definitions of quality. So each of you has your own idea of what soil quality, soil health is, but it doesn't necessarily mean that the person that you would be talking to or engaging with has the same view of what it is. So, and why this is important is because it sets that context of how we operate and interpret information. So I put this in the context of water. If you think about water, if you think about something with excellence that might not necessarily have a standard, you might think of the difference between Perrier water and fizzy water. Something that does attain a high standard, you might think of the difference between ultra pure water and water that's not. You can also think of something that has zero defects in the sense of having no E. coli in your water. So that would then provide a threshold. It might be that you want to maintain things within a range, and that's quality in terms of consistency. Fitness for purpose is very important. So an athlete might choose to have isotonic water in preference to tap water. And then comparisons with value for money or transformative might be the difference between what is ice and what is liquid. So there are different ways that we can look at and interpret quality. And so it's helpful that we're all on the same page. And this is important because it affects or it leads into the scales at which we are interpreting information. So many indicators are scale dependent. They may work regionally or nationally, but at larger scales, it might be more challenging. They might be habitat dependent, or they might be purpose dependent for specific areas. So it becomes important, this idea of scale in choosing. And so as part of the work, we looked at this idea of total soil quality management and thinking about this general framework of defining a goal, then starting to think about what sort of monitoring and assessment might be appropriate, working within and selecting an appropriate quality framework. So what's the purpose of what we want to achieve? What spatial scale would that be at? And who are the target stakeholders that we want to inform? And this should lead into improvement as part of this continual improvement process. So here we are looking at different framings of soil quality. So many people who work at the field scale will be used to this idea of fit for purpose. So it's really aimed at soil managers, example, Cornell soil scorecard. And it has thresholds and indicators usually which are relevant to, say, a particular crop. And that's how we would be interpreting the indicators, or it might be to do with woodland, for example. And so it's very purpose driven, and you need to define the purpose. Whereas when you move up to the scale of national or continental, as we have been working with JRC, they use a different framework, which is this kind of free from degradation. So it's thinking of quality as framed in the absence of degradation, and it's more of a binary choice. So you set indicators with thresholds, and you're above or below a threshold, very much aimed at policymakers to understand where there are issues or not. Then there are other forms of a framework. The external benchmarking looks at a distribution. It's very useful for soil managers because it casts a lens. You take the population of data in an area and you can look at where your farm sits in comparison to lots of other farms, and forms part of that continual improvement kind of process. And then there's things like value assessment, where you would be looking at ecosystem services, natural capital, and seeking to employ some sort of value basis to make judgments. So you can see how these different indicator approaches are used. the European Union Soil Observatory has its dashboard, and it lays out what indicators it uses within its framework. On the top right, we have some thresholds, for instance, that are used when they're crop specific, and that would be a fit for purpose framing. And so the interpretation, they use the same indicators, but the interpretation could be quite different. And the benchmarking approach in the bottom right shows a distribution of national data and what is typical and what is below or above typical. And then you can see where you sit as one of these lines in comparison to others. So it gives you a lens for things that you can't normally see. And so when we get into the business of AI and thinking about the sort of mapping and what have you, then we start to employ the framework, in this case, the free from degradation, and thinking about what is degraded soil, the sort of scale of operation where we're looking at this pan-European scale. And Mehdi's going to be talking later on about how we've been doing both the state and change in order to try and interpret at this scale and combine indicators within an AI framework that is suitable for this sort of scale. External benchmarking is well worth thinking about as a tool for soil managers, because it offers this idea of having a set of data at a large scale that then, if you have local scale data, you can see where you sit. And on the diagram, you can see the distribution of data. You can see that if you were in the blue area, that would be above typical. And you would see that if you were in the red area, it would be below typical. And you're not trying to achieve a certain level. This fits in with continual improvement, where you're always trying to get towards the upper end. And often it can start a conversation about how do I achieve that? How do I draw that into my management to improve? And as everybody improves, the distribution will shift. So it's a moving target. So soil quality and soil health, they're words that we often use. Soil health is great for starting a conversation when you think about what's a healthy soil and talking with stakeholders. But the soil quality, in the way that we've been working with things, is very much purpose-driven, is thinking about, is it fit for the intended purpose, whereas we view soil health as more holistic and intrinsic. Is the soil vital as a living ecosystem in the context of the soil formation setting? So the EU's definition of soil health, I just given here the physical, chemical, biological condition determining its capacity to function as a vital living system and to provide ecosystem services. So it tries to capture and bring together these ideas of both quality and health. Just differentiating, you might think of an alpha soil, a sort of brown soil, cropland soil. It might be high quality for production, but it might be low health due to the presence of lots of pathogens or excess nutrients. Whereas we might view a podsol as being very healthy because it's in its native setting, but we would consider it low quality for agricultural production. So in essence, the framework in the EU is trying to maintain this idea of a consistent health within a sort of excellence framework within ranges. So it's thinking of that consistency, and then it also uses this idea of fit for purpose. So whatever it's being used for, and also that it's free from degradation, the sort of zero defects. So you can start to see how the different framings play out, and the purpose of being able to communicate in this way and to split the different the different framings up is that we tend to then not talk at cross purposes, because when you're looking at different scales, you come from different directions. You can easily find that you're talking at cross purposes. So by specifying the purpose of your indicators and going through a selection process, it makes it clear as to what they're for and how they are being used. So thank you very much. Do come and see what we do in AI for soil health, and many partners who are involved. I think there's over 120 scientists around Europe who are involved. We work closely with JRC in what we do, and this is the paper that we published on this framework setting earlier this year with all the co-authors led by Grant Campbell. So thank you very much.
Fantastic. Thank you very much, David. I'm going to move on now to introduce Mehdi Afsar. Holds a BSc and MSc in Water Engineering and Climate Resources Engineering from Urmia University, Iran, and a PhD in Civil Engineering, Water Resources from the Middle East Technical University in Turkey. His academic career includes roles as a postdoctoral researcher at the University of Manchester and the John Innes Centre in the UK, followed by an assistant professorship at METU in Ankara. Since August 2023, he's been working as a research associate at the Technical University of Hamburg, Germany. Mehdi's current research focuses on developing data-driven tools to monitor and predict soil degradation risks under changing climate and land use conditions. By combining field data, machine learning, and spatially continuous environmental data sets, he aims to identify degradation hotspots, understand environmental drivers, and contribute to sustainable land management practices. This presentation is titled Climate and Land Cover Changes, Impacts on Segregation. So over to you, Mehdi.
Thank you for your introduction, Adrian. Yeah, today I am going to present our recent work on the impacts of climate and land cover change on soil degradation. And I think I don't need to talk about the threats that soil degradation poses on different aspects of our lives, but I want to talk about the objectives of my current presentation, that is, first, to enhance our understanding on the current state of soil degradation and also to predict the future dynamics of it under different climate and land use change scenarios. So we used a machine learning framework to link a soil degradation proxy to different aspects of environmental predictors like inherent soil properties, climate factors, and land use fractions to develop a machine learning framework. And after passing training and validation phases related to that, we used our developed model to predict the current and future soil degradation risks under different scenarios. So given that the main importance of our machine learning framework is coming from our target variable soil degradation proxy, I will try to tell first what is soil degradation proxy and later go through different steps of this framework. To develop our soil degradation proxy, we used 4 soil health indicators of erosion rate, electrical conductivity, soil pH, and soil organic carbon. And in the first step, we rescale each indicator that are representing each one aspect of soil degradation, like chemical, physical, or biological degradation, to the scale of 0 and 1. And after summing them up and dividing the summation to 4, we reach to a continuous proxy between 0 and 1 with higher values closer to 1, showing higher risks of degradation. And how we rescaled each indicator? Namely, we considered a positive relationship between erosion rate and EC and soil degradation proxy, meaning that with increasing erosion rate, the risk of degradation will also increase. And for soil organic carbon, we considered an inverse relationship, meaning that healthier soils in our framework have higher soil organic carbon. For soil pH, we consider biodirectional relationship with centering on 6.5 and going toward left or toward right would increase the risk of degradation. And after summing and reaching to an index, here is the current state of soil degradation over Lucas observation. On the left, you can see soil degradation proxy map for the year 2015. On the center, you can see the map of SDP for the year 2018. And on the right, you can see on a scatter plot of SDP 2015 versus 2018. So overall, looking to these maps, you can see that, for example, at the moment, at the current state, northern regions of Europe has higher soil health information, and most of degradation risks are accumulated around Mediterranean region. And also comparing the scatter plot of SDP within the years of 2015 and 18, showing us that over these 3 years, most of the points are remained the same in terms of their score, but there are some hotspots or the scores that increased or decreased in a sharp way, motivating us to use a machine learning framework to also project this SDP for future and end of century over across Europe. So to get a little bit of more information that what this index or this score shows to us, we tried to show some Google imagery over different land use conditions. For example, on the left, you can see the SDP for a cropland with a value of 0.20, and in the bottom, SDP of again over a cropland with SDP equal to 0.94. And you can see that higher SDP shows higher source of higher risks of soil degradation. And on the right, and another example for the forest, you can see the lower SDP, a good dense forest, and in the bottom, again on the forest land use condition with higher SDP, showing a lower density of vegetation cover. So after getting a little bit of more information that what this SDP value shows to us, and considering that we also wanted to link this SDP value with a machine learning framework to different environmental factors, I wanted to also show what input variables we used in our machine learning framework. We used land use fractions coming from land use harmonized 2 model. On the right, you can see the difference of projected land use conditions compared to historical values, and yellow colors on the right on the maps are showing a gain, and dark blue showing a loss. And a very basic example on the right, for example, we can see that in the future projections, land use harmonized model projected over this area, we will lose annual crops fractions, and instead we will gain secondary lands. Apart from land use fractions, we also used climate data like average temperature, precipitation, annual precipitation, and also surface soil moisture coming from SMIP6. And also we used inherent soil properties like digital elevation model and also soil texture. We have 3 time periods in our analysis, one historical, near future, and also far future. We used 18 different global climate models. We used 2 shared socioeconomic pathways, one for intermediate and also one scenario for higher emission rates. And we used random forest regression to model this framework. We use Lucas observations in roughly 17,000 data points, but we filtered them to those observations that did not change too much between years of 2015 and 18. These filtered our observations to roughly 7,500 points. We also used to split our dataset to 70 and 30% for training and validation portions. So here is our results. On the left, you can see the historical maps predicted by our machine learning framework. And on the right-hand side, you can see the expected change related to soil degradation proxy for intermediate and higher emission scenario for end of century. Again, I want to emphasize that higher SDP value means higher degradation risks, shown by red color, and on the right, brownish colors, meaning increased SDP value, means increased in degradation risks. So looking to the graphs and the maps, we can understand that those Northern European soils that earlier had healthier conditions are expected to experience increments in their SDP value, and those there are some also positive expectations for us that those locations around Spain or those some regions around Italy that earlier had higher SDP values might experience to get toward healthier conditions. To get more information and help policymakers to look after what indicator, we also use some diagnostics in our machine learning to find out what is going on and what is the drivers and which is the governing indicator that yields the change in future SDP conditions. On the left, you can see the drivers of the change, whether it is coming from climate or land use change. And you can see that most of the points are in orange colors, meaning that increased SDP values according to the climate factors. And those projected healthier conditions in Spain and also Italy are mostly driven by land use change. On the right, you can see the governing indicators showing us to that most of those increment in SDP values are linked to the increase in SDP related to increased risk for SOC, meaning that we are losing SOC in future, and also some of them are related to increased in erosion rates. And when we are experiencing an healthier condition, most of them are related to decreased in SDP related to pH, meaning that earlier these regions had higher pH values in future due to the land use condition change are expected to experience and decrease in their pH value going toward neutral conditions and later gain some SOC, and in our framework they expect to have healthier conditions. Yeah, as a concluding remarks, I should say that by end of century, we might, depending on our results, we expect to have more than 50% of Lucas observations to experience increased SDP values, meaning increased soil degradation risks. Most of these are in increments are in cold forest regions in Northern Europe, and there are rooms for some to be optimism and think about the going toward healthier conditions in southern regions, mostly driven by land use management practices. And I want to conclude my presentation with acknowledging AI for Soil Health for funding this this work and also presentation. And also I want to thank all my colleagues that are collaborated with me for during this work, and also all GHI members that I work there. Yeah. That's it.
Thank you very much, Mehdi. That was very interesting. Lots of detail in there. I'm sure we can field some questions around that later. But first, we're just going to go back to Mentimeter with a question for you all, which will be appearing on the screen shortly. So, yes, do you use Chat GDP Copilot? Do you use derived products, e.g. maps? Do you use image recognition, e.g. disease detection? Just get a little understanding of good. Again, a good range. Give it a little bit longer just to. Great, thank you very much. Right, we're going to move on now to our third presentation from Emanuele Legato. Emanuele Legato graduated in agricultural science at the University of Padua in Italy in 1999. He received his PhD in environmental agronomy in 2005 after having completed an exchange period at the Colorado State University in the USA. He's worked and collaborated with many national and international research institutions on several cross-cutting issues related to carbon and nitrogen, biogeochemical cycles, and natural climate solution for climate mitigation. In 2012, he joined the European Commission Joint Research Centre, where he's currently working as Project Scientific Officer on the climate and environmental dimension of agriculture, with a focus on soils. He's author of more than 100 papers in peer-reviewed journals, including in Science and Nature family journals as leading author and highly cited research 2022, 23, 24 in the Clarivate list. So we'll be talking on lessons learned in predicting soil organic carbon with AI and process-based models. So over to you, Emmanuel.
Thank you, Adrian. I'm sharing the screen. Okay, hope it's fine. Please confirm.
Yes, all good, Emmanuel.
Okay, thank you a lot. Thank you for inviting me. And today I want to talk about the lesson that I learned and we learned collectively in predicting the soil organic carbon with artificial intelligence and process-based model. I hope it will be interesting and generate a bit of food for thought. So we all know that soil organic carbon is a very important soil properties, often used to score the soil earth and also we know that it's supporting many functions. Not going into detail on this, but I just wanted to say that there is now a high interest in predicted the soil organic carbon in space and times, also renewed by this CRCF, the Mobile Carbon Certification Regulation, that wants to create a business model for farmer recognizing some carbon credit when they apply management practices and they are able to, of course, sequestering carbon. So my impression was that there is now a lot of AI application for predicting the SOC, and for this I made a very quick search on Scopus, which is an engine search for scientific paper, and I put this word, soil organic carbon and machine learning and spatial, and I got more than 500 documents and including also some deep learning methods. And in general, we can see an exponential growth of paper that utilize machine learning and deep learning to predict this organic carbon. This is not an extensive search. I didn't check any paper, but I just want to have an idea of the order of magnitude. And I repeat the same string search, substituting the word machine learning with the process-based or mechanistic. And as you can see, we found that the use of the model is more constant, I would say, during the last decades. But in particular, we can observe that the number of paper are much lower, about 6 times lower than the machine learning application. Then I repeat the same search and I change the word spatial with the word temporal to see if machine learning used to predict also the change in times of this organic carbon stock. And as you can see, there are less paper, but in the last 2 years, a very dramatic, I would say, increase. So it's more and more use. While again, for what concerns the process-based and mechanistic model, we see that sorry, the use of model is more constant in times, and we can see that also the difference between these two methods for predicting, let's say, spatial temporal changes of organic carbon are more equal. So the model is still used. And so I just put some question now, and why AI is exponentially being used. Are all the AI methods used properly, or there are some methods that are more suited for spatial or temporal prediction? And I would like to try to discuss during this presentation about this question. So first of all, we learn a lot here at the JRC using the Lucas soil points. They were already mentioned. So we are talking about a huge standardized sampling, and we have even more data now with the 2022 campaigns under analysis. But this is one of the reasons also AI in general is more used, because artificial intelligence need data. No, is the foundation of any machine learning, deep learning methods, and there are more data available, not only Lucas, a lot of other data, and particularly also remote sensing data that are often used as a covariate into the machine learning application. And okay, when you have a lot of data, it's more easy. But there is more challenging when you have, let's say, lower data, and this is often the case when you want to predict something that is not common measure, and this was the case when we wanted to partitioning the total soil organic carbon into what is called particulate and minerals associated carbon. So we select from the whole Lucas sampling points 400 representative sample. They were selected by stratified sampling, light hypercube, and we measure we measure by separation the two fraction, the particulate and the mineral associated organic carbon, and which is so we couldn't manage more than 400 sample, because it's require a bit of work, and it's very expensive to separate these two fraction. And just to give an idea how they are useful, we follow a bit the hypothesis that made by Professor Francisco Cotrufo some years ago, that postulate that liter quantity and quality is driving in a different way the particulate and the mineral associated organic carbon formation. So liter of lower quality, the Agar-Steen ratio, no, it's accumulate preferentially as particulate organic carbon, which stay in the soils and takes more times to be decomposed. while higher litter quality can be really fast assimilated by microbial organisms that transform the soil organic carbon, and the bioproducts, the necromass of this carbon is easily so bound to the minerals, to the mineral surfaces, like to the clay, to the silt, forming this mineral-associated organic carbon, which is stay then in soils for a longer time, as a longer resident times. But there also we postulate that this fraction can saturate. So at a certain point, the mineral fraction cannot bound no more organic carbon. So it's called carbon saturation. This to give you an idea of the framework. So we took this 400 sample and we apply a random forest regression, a typical, very well commonly used machine learning method, and we produced two continuous map of particulate and mineral-associated organic carbon at 1 kilometer, so resolution. And we ask ourselves, okay, but how representative are these those maps that, as I said before, continuously represent the two variables in space? If we look at the sample distribution, this 400 sample distribution across the Lucas dataset, we see that they are well distributed into the textural range of the Lucas, although there are some probably area, so high clay soils are not completely covered. And they also, let's say, the distribution in terms of organic carbon follow in quite a, let's say, in a quite good way the distribution of the Lucas soils. Of course, we limit our analysis to 100 grams per kilogram, so because it's a mineral associated organic carbon framework. And we do a lot of cross validation, and the model perform well. But also when we plotted the mineral associated organic carbon versus the total SOC, we identify a kind of threshold that we suggest is to be a kind of saturation, no? As long as the organic carbon increase at a certain point, the mineral associated organic carbon is no more accumulated. So the carbon is no more accumulated into this fraction. And this generates also a sort of a scientific debate if this is, let's say, the upper limit for the European agricultural soils. Our other colleagues from Germany suggested that they have soils with higher soil organic mineral associated organic carbon content that are in this area. But the fact is that we never claims to have detected, let's say, the maximum limited. We just say that considering our data and the distribution of our data, that probably are reflecting a representative of the most, let's say, common condition in Europe, which are dominated by 2-3 soils. This behavior is still valid, and it doesn't necessarily mean that if you have high clay soils that are not represented, the saturation is not valid. And that's lead to me to the fact that there is an interlink between the data representativeness, the scale at which we try to make prediction, and the interpretation from the user. Because sometimes we use now with the few data to go to very high resolution, and so people say, okay, if I have a map of 10 meters of a process, it means that the authors are enough confident to predict at that level. But maybe it's not true. It's a simple, let's say, IT. I call it IT upscaling, no? And so, or we probably don't mask the correctly the area that can be out of the domain. There is this interest paper that also show that. Sorry. And this is particular true for global scale study where we have very cluster data across a temperate region, and sometimes we have prediction in area where you don't find any data. So the distance sample to prediction, the two distribution are very different, where the citation can be like this, where we have equal distance sample to sample and sample to prediction, which is probably the case of the euro. But in any case, predict the model outside the training domain is always a risk, and is often done, especially at, let's say, global level. And another risk is to go in too much high resolution. As I said before, we often now see map at 10-meter resolution, and we need to be aware how much, let's say, our data represent this scale. For what concern then the temporal prediction with machine learning, I wanted to give you this example to make you understand. So let's imagine that this is the carbon stock, and this is the year, and these are Lucas sample, and let's imagine that these are the true values, no? Okay, as if we can take an enormous number of sample. So what happened that when we apply some process-based model, like DayCent or other model that we usually apply at European level, especially if we do some spin-up before, so it may be that the model is inaccurate. So it means that is a bit biased, far from the true, from the reality. But if you want to predict the soil organic carbon changes, maybe the model is precise. In general, the process-based model are mass balanced, so they provide what reliable simulation of SOC changes in times, if they are, of course, proper calibrated and properly used with the right input. While with the Lucas, we have often this situation where we have for 3 data, let's say a lot of noise in the samples, in the values, and these are pure error, no, derived from collection for analysis, etc. Especially because the Lucas is not designed to monitoring the SOC, the organic carbon stock. So Lucas, in the average, may be more accurate, but the difference between one Lucas and the other can be many times just pure error, pure noise. And so my take-home message is that temporal prediction with machine learning can lead to inconsistent outcome if data are noisy, because the machine learning wants to anyway try to fit the data in any case, while process-based model are more mass balanced, consistent, and so guarantee a sort of understanding of what is going on. Although models are not perfect, and they can miss processes, and in fact, when we use the MENS model, which is a organic carbon model, which predicted the fraction that I mentioned before, the particulate organic carbon and mineral associated organic carbon, and we calibrate the model with the same 400 sample, and with 2 calibration methods, which I'm not going to explain, but we obtain 2 different set of parameters. So, which is quite somewhat challenges, and we ask why. But when then we predicted the soil organic carbon difference between the measure and the model values for the other Lucas, for the Lucas not used, of course, in the training dataset, we observed that one method was, let's say, less biased, this one, but underestimating the mineral associated organic carbon. This method, the Monte Carlo Markov change, was a bit more biased, but was able to better estimate the mineral associated organic carbon. So there was a bit a trade-off between these two to predict the total soil organic carbon on the mineral associated organic carbon. So that means that probably the model are not still perfect, and we probably need more, if you want, I would say, in my opinion, local calibration for different, at least for different mainland cover. And just to conclude now that in view of the carbon farming certification, in particular, when we want to go at a very high resolution and having the change of soil organic carbon at parcel levels, the use of remote sensing to drive the models or to be assimilated in process-based model is very promising, because now with the Sentinels we have 10-meter maps and we can derive many proxies, many indices, calculate the MPP or calculate the different indices and assimilate it into different models. And with this we can feed then soil organic carbon model that to somewhat predict the soil organic carbon changes. So in a very, I would say, mass balance way, so consistent mass balance way, and we know what's happening. So to conclude, artificial intelligence methods are exponentially used for soil organic carbon prediction, particularly in space, but now we see also many spatial temporal application. We have to be very careful anyway on the representativeness on our dataset. How we extrapolate, we need to be still into the training domain. When we extrapolate the data, there is a lot of issues on the cross validation that are not talked about, and also a bit of circularity in the sense that sometimes we use a lot of covariates that come they say from modeling. So we are modeling a model sometimes. On the other hand, process-based models are evolving, and they ingesting high resolution input, in particular for observation, and there are new data assimilation schemes. And the last frontier is they try to combine, let's say, the strength of the two methods, the artificial intelligence and process-based learning, with this hybrid modeling. And that's for my presentation. That's all. Thank you a lot.
Thank you very much, Emmanuel. Some good questions in the middle of that as well. Hopefully has got some people reaching for the Q&A to ask you something, to follow those up. We've got 20 minutes now to tackle some of your questions that you've put into the Q&A. If you haven't already submitted them, please do so. Use the Q&A tab at the bottom of your screen, and we'll try and get through as many of those questions as we can. Just having a look at the questions, they kind of come in sequence in terms of the presentations, and there are several questions there for Mehdi. Mehdi, would you like me to read the question out and then you answer it, or is that how you prefer to go through this?
Yeah, I can go one by one.
Yeah. So. Hi Mehdi, I'm Fatima from Remote Sensing team from Hamburg Uni. Thanks for your nice presentation. Did you check the transferability of your model? And there's a second question following from that. What was the model used to evaluate the upcoming prediction of land degradation?
Okay, in terms of model transferability, I think we use Lucas observations to develop model and also evaluate that. It is really hard to say, okay, we train this model, now you can use it in another continent. I think it would work, but it would be in comparison to Europe. So the reference is the Lucas observation. But we didn't test our framework in another continent or with other data sets. And for the you said about the model to evaluate the prediction of land degradation, we use some statistics like R squared or root mean square error, but for the current state of prediction SDP, not for future, because of course we do not have data sets of real observed SDP values for future projections, and they are basically based on scenarios. But for the current state, we compared the predictions of our random forest model with our observations, and we reached to R squared of 0.58, 59-ish. I think you are muted, Adrian.
Thank you. Following from that, a question from Deepak Yadav. How did you select the soil health indicators, and what were the main criteria or basis for their selection? And following from that, moreover, soil compaction is becoming an alarming issue. I think it would be great if we could find a way to integrate soil compaction into the assessment framework. What are your thoughts on considering soil compaction as an indicator of soil degradation? So there are sort of two questions there.
Yeah, okay, so our motivation for selecting the soil health indicators of erosion rate, electrical conductivity, and soil pH and soil organic carbon was to represent every aspect of soil degradation. So we picked soil erosion rate, for example, to cover physical degradation, electrical conductivity, to chemical degradation, and soil pH for biological degradation. And following Emmanuel's presentation, we could also see that soil organic carbon already covers all three aspects of soil degradation. And in terms of soil compaction, we can add any indicator we want, but we didn't want to give more weight toward physical degradation. We wanted to keep equal weights for each aspect of soil degradation, but the approach or the way we construct soil degradation proxy allows us to integrate any other indicator we want to add to it.
Thank you. And you've partly answered, but mineral associated organic carbon is also applicable for total soil total carbon, question mark?
I think this is not mine. Emmanuel can answer that.
Okay.
Yeah, I'm not sure if I understand well the question, but the mineral associated organic carbon, it's a component, a fraction of the total organic carbon. Often in mineral soils, a very prevalent fraction because it's a kind of stable fraction, and so soils, agricultural soils are often perturbed a lot. So the POM, the particulate organic carbon, is more prone to be decomposed and quickly, and the one that is associated with the mineral bound to the mineral matrix can stay in the soils longer, and so this is my reply.
Thank you. Maybe there's a technical question around the impact of ordinary Portland cement, which may be something you might want to type your answer to. So it could be a little bit too technical. We can come back to that. I want to just go back to two questions from an anonymous attendee, which is sort of close to my heart. I didn't really introduce myself properly. I'm an organic farmer. I've been working in farming and food for over 30 years now. And I'm really interested in the applicability of this to on-farm policy in relation to agriculture, as well as potential land use change in terms of tree planting. So there are two questions here. So I'm not sure who would want to pick these up. I imagine David and Emmanuel would both want to have a go at this. Do you think we will be in a position where we can use these predictive tools at a farm level, for example, to help farmers plan which plot of land to plant trees, or the benefits of practicing cover crops, so a farmer could feasibly get advance payment for carbon sequestration using the model's prediction? So who would like to have a go at that? Emmanuel.
Yeah,
Okay.
I can reply to the first one. Just to say that indeed there's a lot of modeling exercise, modeling in a broad term, process-based also machine learning, where at a larger scale, when the impact, the application of different practices as a scenario is done, and to assess the overall effect. Now, I guess the carbon farming regulation, the carbon farming market will trigger the application of this method also at the farmer level, because at the end is where now you account for carbon credit, and I think this can really benefit also the farmer that apply for the certification, because there will be already a plan and simulation to understand which practices can be best to sequester more carbon.
David.
Yeah, I can come in on that as well. Yeah, so there's already tools out there. So for the UK, UKCH produces something called the ePlanner, which is a free-to-use tool, and you can go in and it helps you to understand where to place interventions in the landscape.
David, would you be able to put links to that or other things into the chat? That'd be possible. And then I think the next question, I think what I would like to probably refer on to you as well. It looks like most of the indicators trialed with machine learning are physical and chemical still. Are there studies looking at biological indicators? How would that work with the complexity of the soil web? And I note that the EU's definition of soil health means a physical, chemical, and biological condition of the soil, determining its capacity to function as a vital living system and to provide ecosystem services. So I'd be interested to hear your response to this question.
Yeah, I can have a go at that. So I think it's important to point out that the work that Eddie was doing in collaboration with others was really thinking about the proof of concept of how you can combine indicators to get both a single index and also be able to look at the individual indicators in terms of attribution. And that's where the piece of work was very successful. It only has 4 indicators because it's proof of concept. So it doesn't take all of the indicators. We took, as Mehdi was saying, we took ones which we thought were critical, but also in the combining in the slide that he presented, some of them are increasing as you go up, some of them are decreasing as you go up. pH, for example, is an optimum. And so how do you combine that sort of information together? And what the work was able to demonstrate is that it is feasible to do that, and then you can start to bring in other indicators. So yes, compaction definitely would be one. How do we do it is a question, and biological is another. And so you need biological change data that you feel would be reliable, whether that's some kind of index, some sort of Shannon index of biodiversity, or whether that's something else, I don't know, a distribution of sort of earthworms maximum. The difficulty with these things, the biological indicators specifically, is once you get up to this transcontinental scale, there's not necessarily some underpinning aspect that means that they're suitable in all places, whereas you might think detection of erosion, pH is suitable at continental scale. And that's when it comes back to this issue of scales. What's the purpose and how are you going to apply it? So some of the biological indicators can be incredibly pertinent at the local scale, but might not scale up to national or to transcontinental scale.
That's really interesting. I'm going to just link another further question and come back to Emmanuel. So, hi Legato, I'd like to follow up regarding the contribution of plant-derived SOC to the mineral-associated SOC pool. Can you please clarify your perspective on this? And then perhaps you want to comment more on the biological indicators too.
Yeah, so I will put in the chat maybe the relevant papers the audience can better understand. A few words, I would say that of course the more inputs you have, the more carbon in general you have. Okay, it's not a strict relation, but also not only the amount of input, but also the quality is important. And if you have high quality litter, what does it mean? Quality with high nitrogen and low lignins or residue with high, let's say low CN ratio. I don't know, for instance, typical leguminous crops or yeah, stuff like that, or also general residue with the lower CN ratio. Which have a lot of components that are soluble and that are very easily uptake by microorganisms, no, for their use, and so the product, the bioproducts, the necromass, whatever comes out from the metabolism and catabolism of that, somewhat it's really easily attached, bound to the mineral matrix, becoming mineral associated organic carbon. And it's clear because from many laboratories we see that the organic carbon that is associated to the mineral matrix is more close to the let's say microbial origin, although you can also have plant components of low molecular weight. But if you see the CI ratio of this also fraction is more close, let's say, to microbial than to the plants. It's really derived from the transformation of the soil organic carbon by microorganisms, which is the primary, let's say, driver of the soil organic carbon transformations. So the more, in theory, you put a residue, a liter of high quality, the more you expect it to have a bit more of mineral associated organic carbon also.
Thank you. Mehdi, there are a couple of questions for you coming in. One of which is, did you use a data set from any particular season, for instance, the summer season?
Not exactly the summer season, but for predicting the current and also future state of STP, we averaged climate and also the land use fractions for the last 30 years. Like if we wanted to predict the year 2015, from 1986 to 2015, we averaged yearly annual precipitation or average temperature to get roughly idea about the climate factors correlating with STP. We did the same also for future projections.
Thank you. So I think we have now run through all the questions. There was the one about what is your, to you, Mehdi, what does your data reveal about the mechanism and extent of soil degradation resulting from ordinary Portland cement exposure? Do you want to talk about that now, or something you'd rather do a detailed response to RMT Cameron?
But this is too much detailed
Yeah.
questions. But just for one example, if Cameron remembers the decrement in STP in across Spain, it was mostly related to land use change projected for that region. So land uses say that with the human pressure on croplands would decrease on that region, and this would turn to secondary lands like grasslands or shrubs, and then hence the soil pH would decrease because of less inputs of fertilizers, and when pH goes toward neutral condition, SOC accumulation happens. And so there are too much detailed processes there. We can have more detailed discussion in private.
Yeah, thank you. There was a question around EU-wide activity and whether the EU itself was too limited a geographical area. I think that's been answered. I think that the answers that you receive are personal to yourself rather than available to everyone, but I think that will be picked up in the recording. David.
Yeah, I thought it would just be worth sharing quickly the work that Tom Hangel's done at OpenGeo Hub. So if I can just share my screen. So I think hopefully this will be of interest to folks. So this is one of the outputs that we have, which is the Eco Data Cube, and OpenGeoHub in the Netherlands have produced this. It has the input of Lucas data, but it also has data sets from other countries. And there was a question asking about how we could contribute. So data that goes into data sets that go into OpenGeoHub and that can be ingested can contribute to this effort. They call it 3D plus T because it's able to go back in time. So it does about 20 years. It does different depths. So you can go down the profile. And these are all AI predictions based on the data that's available. Moreover, it can be shown that you can see how a particular metric appears in time at a particular location, and with depth as well. So that was soil pH, and so things like bulk density. Somebody was asking about compaction. So that's been mapped, and organic carbon, for instance, has also been mapped. And there's multiple layers in here. I think it's important that people remember that because it's AI data, there are issues both with the data in terms of being, looking at this and how the data is combined. As Emmanuel was pointing out, that accuracy and that precision vary, and there are also issues with how you predict. But in terms of looking at the future, I think of AI generated soils information, the data cube really starts to be able to show us how we can get at combining this data into making state and change predictions. And because it's an open platform and open data, and all the data is freely available, all the data layers, we can start to understand where the issues are, what the problems are, how it relates to further data on the ground in regions, to try and make it better and better. So the more data and information that goes in, the better it should become. So I'll stop sharing there.
Thank you very much. That was a really useful presentation. Thank you. We've now just got to the point where we've got our final Menti question, which will be appearing on your screens in a moment. So what impact do you think AI will have on the future of soil health? I think this is a free for all answer. There's no scale here. We just put the link back in the chat to the Menti. So I think while you're filling that in, I can just begin to make my sort of concluding comments about the webinar and the presentations that you've heard today, looking at sort of key takeaways and reflections. I feel, first of all, I'd obviously like to thank all our speakers for being so clear and containing such a lot of interesting information. And clearly this is a very important project, and lots of moving parts within it. As I say, there's a 5 webinar series if this forms just one part. And I would definitely recommend looking back at the 2 previous ones, you haven't seen those, and booking ahead to the next the next one's coming up. I think that in terms of key takeaways and reflections, I think from David's, there are sort of three main points to come from that. There are different soil quality frameworks, and they vary across scales and have different purposes. Soil indicators may be interpreted differently depending on scale and framework, and it's important to define a quality framework which will therefore aid communication. And moving then to Mehdi, I think the main points that have come from his presentation. Soil vulnerability across Europe is projected to rise sharply. By the end of the century, more than half of all sites, 54%, could face higher degradation risks under high emission scenarios. That's a very worrying figure. Climate change is emerging as a dominant driver of soil degradation, with warming and more extreme weather putting increasing pressure on soil systems. Well, I can certainly say that's within my experience of the extreme weather we've had in the last 12 months in the United Kingdom. There is room for optimism. Adaptive region-specific land management strategies can help counter these impacts, strengthening soil resistance and supporting sustainable land use across Europe. And finally, Emmanuel's presentation. Again, the main points. AI models are increasingly used for spatiotemporal soil organic carbon predictions. That's very, very clear and rising dramatically. Since many AI methods are black boxes, any application should pay attention to data representativeness, extrapolation outside the training conditions, cross-validation, and model circularity, obviously extremely important for credibility. Process-based models are evolving, profiting from the availability of high-resolution remote sensing data that can better inform carbon models. We will be uploading the recording of the webinar to YouTube shortly, and we'll email you all with a link. And if you have any additional questions or would like to find out more about the AI for Soil Health project, then please visit the websites, links in the chat, or you can reach out via their social media platforms. We'd love to get your feedback on today's event. A link has been added into the chat with a few short questions about your thoughts of today's event. Please do take the time to give us your thoughts as it can help us to improve for the future ones and monitor our impact. We'd also email you the link in our post-event follow-up. The next webinar in the AI for Soil Health, Envisaging the Future of Soil Health Monitoring webinar series will be on the 12th of November, called Building Soil Monitoring into Policy, digging into the EU soil monitoring law. So do register now for a free ticket by following the link in the chat. All that's left for me to say is thank you for joining us. Please do fill in the feedback form that we've posted in the chat, and we hope to see you for our next webinar. So thank you very much.